Okay, here we go. So look, I'm going to start with this circuit. There's the solution to that, but I'm going to move through these quickly. Let's see if we can do these three. Let's say 10 minutes each. Okay, ready? Here we go. So I'm going to go right down the line. I'm going to start with example right here. Okay, so here's my circuit. So if I have nice numbers for these values here, let me tell you, that typically means nasty roots. Okay? I mean, it's hard to get clean roots, but here we go. We want to get the current of the inductor. Okay? Here we go. Let's derive it quickly. Okay? Let's derive it quickly. So what am I doing? I'm going to get that current. How do I get that current? I'm going to use KCL, KVL. So what variable am I looking for at the end? Equation 2 is the derivative of that inductor right there. Here we go. I'm going to use the matrix form. So I'm going to apply KCL first. What does KCL tell me? I have the source coming in, and then look at the currents. They split right there. So I get the current of 1 ohm plus the current of the inductor. What is my job? I got to get the current of the 1 ohm. How do I know the current of the 1 ohm? Note that this 1 ohm is parallel to these. So this tells me here that the 1 ohm must be the voltage of the inductor, the voltage of the capacitor divided by 1 plus IL. Okay, so what am I going to do next? I'm going to convert VL, excuse me. So I'm going to get what? I'm going to get L, which is 2. Then I get S hat IL plus IL plus VC equals I source. That's my first equation. Let's go to the second one now. KVL. I have to relate these two together here. And look at, we already did that in essence. What I'm going to do here is that I'm going to use a KVL around this loop here. So the voltage of the constant 1 ohm must be, oh man, there's a lot of ways I can do this. The voltage of the 1 ohm has to be what? Equal to the voltage of the inductor plus the voltage of the capacitor. So how do I get the voltage of the inductor? Note, I already used this loop here. So if I do that, I could run it to be redundant. If I look at this node, here, you can see here that I source must be IL plus I1. Right? I'm looking at this node, I'm looking at KCL right there. Current coming in, it gets split into 2. So I'm going to plug this guy right into here now. Okay? So what's this guy here? So I get the voltage of 1 times the current of this guy, which will be I source minus IL, equals this guy here, which has to be 2 S hat IL plus VC. So look at that. I got everything in terms of VC and IL. So then this tells me here that I get the equation here. Look at that IL. I'm going to bring it to the other side. So I'm going to get 2 S hat IL plus IL plus VC equals to I source. I'm getting the exact same solution. Did I mess up here? Yes.
Yeah, you use this. Can you do something else besides I source equals IL plus I1? Because that's your original equation for KCL.
This one I use KVL. This one here I use KCL.
If you did a source transformation, would that make it easier?
Say that again?
If you did a source transformation, would that make it easier? Because you have one loop, and an IL would equal IC.
Sure, you could do that. But the question is, yes.
IL equals IC anyway, so if you have 2 equations,
Oh, Oh, you know what? You should take my pen and I should sit down. Did you hear what he said? He just says, these guys are the same. There you go. So, look what I'm going to do here. This is the same as that one, right? So it's the same thing. Since I can do this and you can't do this, I'm going to do it. So this tells me here that IL has to equal IC. Which then tells me that IL, look at the IC, I'm going to bring it to the other side. It's going to be minus C, which is 1/2 S hat BC equal to 0. Thank you for the help. So that being the case, I'm going to matrix this guy up. If I matrix this guy up here, so the first thing, I'm solving for the inductor current. So that means this guy tells me I got to look for the derivative of the inductor current. Right? Because that's what differential equations do. Look at that, this guy's right here. So this is my equation 2 here. This is the one that has the variable S hat IL. So now I'm going to matrix this guy. So if I look at that, I'm going to write IL minus 1/2 S hat BC equals to 0. Then I'm going to get 1 plus IL, excuse me. So I get IL times 1 plus 2 S hat plus BC equals I source. So if I write a matrix for this thing, then it should be 1 plus 2 S hat. Then I'm going to get minus 1/2 S hat. And then I'm going to get 1 IL BC equals 0 I source. Could I have written this equation first and then that one second? Yes. So now I want the solution to this guy. So the solution to IL, look at it, it's the first one, it's not the second one. Right, it's the first one. So if I look at the first one here, that means solution to IL looks like this. So it's got to be B IL equals what? Since this is the first one, I take this column and I replace it with the first column, which is associated with the IL. So then I write 0 I source minus 1/2 S at, and then 1. Right? So you can see here, remember, so if I go like this, I get a positive. If I go backwards, I get a negative. So here I go. To get the determinant, I get 0 times 1, 0, and then I take this guy here. So this will be 0 minus 1/2 S hat operating on S source. So that in the end, this is equal to 1/2 S hat I source. So now I got to calculate D. So D is this matrix right here. That's D right there. So if I do that, I got to take the determinant of that. So remember, this is positive, that's negative. So if I look at D, it's got to be 1 minus plus times 1 times 2 S hat. Okay, right there is D. That's my operator matrix, giving me that solution. So then this is 1/2 S hat IS. So now I just got to clean it up. So if I clean this guy up here, I got to multiply through. So that minus and minus is a positive. So I'm going to get 1. My first term gives me 1/2 S hat. My second term gives me S hat squared. And there's my equation right there. So what am I going to do? I'm going to go get the roots. So now I'm going to calculate Okay, so my roots go like this. So this equation gives me whereas my other equation, it should be s squared plus 2 alpha s plus omega naught squared equal to 0. So what I'm doing here is that I'm comparing, right? I'm comparing two equations. If I compare these two equations here, what do I end up getting? Well, what it tells me here, it tells me what here? It tells me that right away, if I look at this, you can see that omega naught squared has to equal to 1, so therefore omega has to give me 1. The question is, what about the second term? The second term here tells me that 2 alpha is equal to 1/2. So then I get 2 alpha equals 1/2. So this tells me here that alpha must equal 1/4. So looking at this combination, omega naught must be bigger than alpha. So if omega naught is bigger than alpha, this means that it's underdamped. And without even thinking about it, my solution for the current of the inductor now has to be what? It has to be A1 e to, it's e to the minus alpha t times A1 cosine omega t plus A2 sine omega dt. Okay, so what's alpha in my solution? Well, alpha is equal to 1/4. What is omega d? Omega d, from what we talked about earlier, is sort of the term that reads what? Omega naught squared minus alpha. So I gotta get those two things here. So this guy, if I plug this guy in here, what I'm going to get is that I'm going to get what? 1 squared minus 1/4 square root. So this is not a pretty number. So when you calculate this number, I get 0.968. And these are all, this is in rads per second. So now I got omega g, so what's my solution look like? Well, it should be IL of t. By the way, I didn't get my b value. But for right now, let's look at this thing. So this will be e to the minus t over 4 times the quantity a e s1t. Oops, nope. Keep messing up. A1 cosine of 0.968t plus A2 sine of 0.968t. So that's my solution plus my b. So one thing that I forgot to do here is I should have calculated my b constant right away. So the question is, what is B? Go to the circuit. Look at the circuit here. Look at the current of the inductor. As t goes to infinity, what's the current of the inductor? 0. So by inspection, IL at infinity has to be 0 since cap open. Okay, so we know it's got to be 0. Does our equation tell us that? So what we do here is that we assume IS, the source current, is a constant. Why is it a constant? Because I'm going to give you a constant. That's why. All sources are constant. So now, look at the equation. So if I look at my equation, it's s hat squared plus 1/2 s plus 1 operating on the function like this, which is then equal to 1/2 S hat IS. So what does this equation tell me? It tells me this, that if IL is equal to B, which is a constant, and I plug that right into this equation here, I'm going to get what? I'm going to get S hat squared B plus 1/2 S hat B. And since these guys are derivatives, that immediately goes to 0. Right? Because they're derivatives. So then I get what? Plus B, and then this equals 1/2 S hat of a constant source. So then this guy also goes to 0. So if that's 0, that's 0, that's 0, B has to be 0. So this implies here that B is 0. So when I look at my solution, you can see that this term has to be 0, and so therefore I have this. This is my current right there. So what does that mean? Well, it means this. That I'm going to have some oscillation. And my oscillation is going to be underdamped. And when I calculate the period, let's say I calculate the period from here to here, that period D is equal to 2 pi omega D. What's omega D? That right there. And by the way, you will do this in the lab and measure that. Okay, let's go to the next circuit. We didn't do so hot there for 10 minutes. Okay, let's go to the next one. The next one is which one? Yes.
I think, is it alpha minus lambda or minus omega? Omega minus alpha.
It's omega minus alpha. Okay, for omega. Yeah, because that's how you get the complex roots. So let me make sure I get the right circuit. Okay, here's the next circuit. So now we got what? Example 9.3, what did I call it? B? It's the second circuit. So here I have what are we solving for in this circuit? Is it the current? Yes, the current. So in this circuit here, we're solving for IL. So what's the values that they give us here? This is 4, 6, 1, and then this is a quarter of farad. Let's do this. Okay, ready? Here we go. So if I do this, I'm going to look at KCL, and I'm going to look at KVL. What am I solving for? This guy. So when I go to look for my second equation, it's got to be the derivative of that guy. Note, earlier I was looking at variable 2, but IL was variable 1 as far as our notation is concerned, because I want you to just look at it. So let's do it. So what I'm seeing here, I got to look at all of these currents here, right? KCL has only really one node all the way across this thing. So that means I got to do what? So 5 amps must equal the current of the 4 ohm plus the current of the inductor plus the current of the capacitor. Right? At the top node, that 5 amps is going like this. What do I got to change here? Look at that 4. I got to change the 4. Look at the IC. I got to change the IC. Let's go do it. Then this tells me here that I got to change this. How do I change this? Look at I4. Since they're all parallel, it must be parallel to what? The voltage of the capacitor. So then I go 1/4 VC plus IL. I look at this guy. I got to convert it into an operator. So then this means here it's got to be plus the capacitance times S hat VC. So when I look at this guy here, you can see automatically that right now I have everything in terms of VC and IL. I'm looking good. But I'm not looking good, but this is good, right? So now if I look at KVL, I got to relate the voltage of the cap and the voltage of the inductor. Note that these two are in parallel. So that means that cap voltage must equal the sum of these two. So then I'm going to say VC must equal the voltage of the 6 ohm plus the voltage of the inductor. So when you see here, I have what? Voltage for the 6 ohm resistor, which I got to change, and I see VL, which I got to change. So what do I know about V6? It's in series with the inductor. So that means then I could come in here and write this as 6IL. Okay. How do I convert that? It's got to be its inductance times S hat IL. So then this will be S hat IL, and that has to equal VC. Here's my second equation here. So what am I solving for? The inductor current. I need the derivative of the inductor. Where's the derivative of the inductor? Not here, right there. You can see that that's my equation 2. So now let's matrix this guy up. Okay? Let's look at the matrix. So I'm going to clean this up here a little bit. Let's see if we can do this a little bit faster. See this guy here? VC? See that quarter? I'm going to get rid of that quarter. Because I want easy things when I take the matrix. So I'm going to multiply everything by 4. That becomes 4. That becomes 20. Okay? Here I go. So I'm going to write 1 plus VC, 1 plus S hat VC, right? And then I'm going to get 4IL, and then I'm going to get 5 times 4 gives me 20. That's my first equation. Look at my second equation. See that VC? I'm going to bring it to the other side, so I'm going to get a negative sign. So when I do that, I'm going to get minus VC plus 6 plus S hat IL equals 0. Now I'm going to make my matrix now. If I make my matrix, it's going to be 1 plus S hat minus 1, 4, 6 plus S hat. Look at IL now. It's the second variable, not the first variable. So how am I switching? It's just convenience. What do I think is convenient? Could you have done it the other way? Absolutely. Remember, you figured out what works for you. Here I go. So note, I'm going to start taking a little bit of shortcuts now. We know that this guy is D. And so what I'm going to do here is that I'm going to calculate D right now. Okay? So if I want the solution, it's got to be dx2. Right? That's what I'm looking at. So here I go. So in this case, it's not x2, it's going to be IL times this determinant here. Okay? I'm going to do it right in one step. So then I multiply these two together, and then I subtract these two together. So if I multiply these two together, I'm going to get 1 plus S hat, 6 plus S hat. And then I do this, so this is going to give me minus minus, which gives me plus 4. It's operating on IL, and then I change in my matrix. Since I'm looking for IL, note that it's in the second position. I'm going to take these guys and I'm going to put it in that column right there. So then it's got to be 1 plus S hat minus 1, 20, 0. See? So I'm trying to save some time here. Now I got to multiply out this mess here. Let's see if I did anything right. So here, 1 times 6 gives me 6. And look at that 4. Plus 4 gives me 10. Now remember, don't let me cheat, right? Don't let me get away with simple mistakes here. Now I'm going to go after the S hat term. So the first one gives me 1 times S, gives me S hat. And then 6 times S hat gives me 6S hat. So I get 1 plus 6 should give me 7S hat. And then the next one here has to be the S hat square term. And you can see that's going to be S hat plus S hat gives me S hat squared. That gives me IL. And then this gives me, now I'm going to do this here. 1 plus S hat times 0 is 0. And I get minus 20 gives me 20. There's my equation right there. So what am I going to do? I'm going to go after the roots now. Let's see. Did that work out for me? What do I get? I don't know what I got. I can't see right now. Is that right?
Yeah.
Is that okay? Good. You know, I'm making up all this shit, by the way. Right? Yeah, I remember my son asking some years ago when he was about 7. He said, "Is that a language that you're studying, Dad?" Yeah, it is, right? How many people can speak mathematics? Not that many. Okay, let's go after the roots now. So, next we want to determine the roots. So the roots here, wait, we gotta go get the B constant. We gotta do the B constant first. Look at the circuit. Look at that guy right there. The current of the inductor. What is the current of the inductor at t equal to infinity? Okay, I'm going to do it right here, okay? So now I'm coming this direction. Why? I got space right there. So if I look at this guy here, it tells me that at t equal to infinity, I'm going to get 5 amps. And then I'm going to get a 4 ohm resistor. And then I get a short here. And then I get an open. So what I'm seeing here is that I have a 4 and a 6 right here. But now the inductor current is going where? Right there at t equal to infinity. So what I'm seeing here is that the current of the inductor at infinity must be the current of the 6 ohm resistor at infinity. So clearly there's nothing here, so what am I going to use? I got to use current divider rule to get that current. So here we go. So the current of this guy has to be what? The opposite current divided by the sum. So I get the opposite resistance. Look at that, I said current. Right? But we're among friends. So we know that my language is all, well, I shouldn't say that, okay? But it's got to be the sum of these guys here times the source current. So look at that. I get 4 divided by 10 times 5. These two cancel out. I get a 2 in the bottom. So therefore it should be 2 amps. So B better be 2 amps. Okay? Look at the circuit. If I put in IL as B, I get the second derivative of B, which is 0. I get the first derivative of B, which is 0, so that in the end, I'm left with this equation right here. So I get 0 plus 10B equals 20. And look at this. Dude, this is sweet. Right? So that looks good so far. So I got my B constant. So what's the force response for the circuit? It goes to 2 amps. Okay? So when I look at my solution here, that means my total solution my B here has to be 2n. So now I want to go determine characteristic roots. So what do I get here? So if I look at that equation here, the roots have to be what? I get s squared plus, I don't even know where I'm looking on this thing. Right? Is that the equation? Oh, I'm there. Can I break this up? Sure we can. That's what I mean by being nice. You look at that, this implies here that S1 is equal to -5, S2 has to equal -2 in order to satisfy that equation. So if I do that, these are real and distinct. This has to be what? Overdamped. Now I could have done it a different way, okay? But you gotta admit, that's the fastest way. But the other way here, I compare this to this guy right here. And if I did it this way, what you're seeing here is that I would pick what? So I know that 2 alpha has to equal 7, and I know omega squared has to equal 10. So what I'm seeing here is that alpha is equal to 3.5, omega naught squared, or the square root of omega, is that. And that has to be less than that, right? Because this has to be just a tiny bit above 3, which tells me that alpha is greater to omega naught, which then tells me overdamped. Okay, and then you would go back and you would go into that equation, and then you would start doing this here. You would do 3.5 plus or minus 3.5 squared. Oops, I got to do the other one. Times, yeah, it is. It's 3.5 squared minus 10. And then you would get those roots. And when you calculate those roots, you would get 5 and 2. But since I'm your friend, I try to make them easy when I can. And that's what I mean by that. So then, what do I mean? That means that the solution must be what? So I go, IL of t has to equal A1 e to the minus 5t plus A2 e to the minus 2t plus the constant 2. That's my solution right there. Yes? Any questions? Let's go to the next one. So now we're at example 9.2 or 9.3c. So I got a switch here. Okay, so it's 20 volts plus or minus. That's so this guy here is quarter F. This guy's oh damn, there's another resistor. This is 1 ohm, and then this is a 10 ohm. And we know the switch opens at T equals 0. So let's think about this physically before we do anything. The thing that's close, what's it going to do? It's going to short this guy here. So then that means I only have one loop, because that short's going to kill everything off right here. So if I now open this switch, what happens? There's no more sources. If there's no more sources, that means my force response has to be 0. Since there are no sources. So when I derive my equation, the right side, the effective source term, has to be 0. It has to be 0. No choice. So if I don't get that, I made a mistake. Let's do this thing. So what does the circuit do? After switch is thrown, then we have what? We have the inductor, we have the capacitor, and we have the resistor. So I have a 1 ohm, I have a quarter F, and I have a 2 Henry. Tell me, what are the directions of the current? It has to be down. Wouldn't you agree that this is the node here? Wouldn't you agree that this has to be the ground? And this node right here has to have some voltage, there's only one. So which direction is the current going? Down, down, down. So where my current's going? Down, down, down. You try to do something different, you're going to get the wrong answer. So now, let's go do it. So I'm calculating, what am I calculating? The capacitor. So let's go do that. So here we go. So I'm going to do KCL. What does KCL tell me? KCL tells me that these three are all pointed towards the ground. So it has to be IL plus IC plus I11. So you can see I have two terms, right? I got to convert the IC to VC. I got to convert that to IC or VC. So then what am I going to do? That has to equal to 0. Now this tells me that IL is good. This guy, I got to convert. So that's a 1/2, so it's got to be 1/2 S hat VC. Let's go to the next term. This is a 1. Note that these two are in parallel. So then that means here that this has to be 1/1 VC equals to 0.
Wait, Skylight?
Yeah.
I think it's 1/4. I think you changed the.
You just copied it.
Okay. If you want to worry about details, I just But I can make those mistakes. You cannot, of course. And then I point my finger at you going like, shame on you how you could do that. Let's go to KVL. KVL tells me what? Well, these two are in parallel. So then I'm going to write VC must equal VL. So what am I going to do? I'm going to bring that to the other side. So then this tells me here that it's got to be VC, but I got to convert VL. VL, when I look at that, it's 2 Henry. So it's got to be minus 2 S hat IL equals to 0. So since I'm solving for the capacitor, what is the derivative term of the capacitor? That guy right there. So this is the guy that we would be calling in that old notation as 2. This is the one that's going to help us in the next step. So let's go do this. So I'm going to matrix it up. So now I'm going to skip a step. What I'm going to do here is that I'm going to just automatically put it into matrix form. So here we go. These two are combined here. So this means I'm going to write 1 plus 1/4 S hat. And then my IL term is going to be 1. No, I'm already setting it up, so this is the way I did it here, is that I'm doing this here. And then what's my source term? 0. That's good. We want a 0. Now let's look at the second equation. Since I wrote VC first, I'm going to write this as 1. The second term here is minus 2 S hat. What's my source term? 0. Beautiful. If I get these C's to be 0, that means that the differential equation has to equal 0. So here we go. So now I'm going to cross multiply, right? Positive, negative. So this guy gives me a negative, so I'm going to get minus 1 plus a quarter s hat. There's a 2 here, so I'm going to put minus 2. So that minus 2, I'll put it on in front. And then I get this cross term, which is also negative, so I get 1. So these guys now operate on VC, and you can see that when I do the right side, I'm going to get 1, I'm going to get 0, 0, 1 minus 2 s hat, and you can see that I'm just multiplying everything by 0, so it's got to be 0. And that's a good sign. So see that minus sign, I'm going to get rid of that. So if I do that, I'm going to get the following thing. I'm going to get, so the first term here, I'm going to get 2s hat plus 3. Is that right? Right? That gives me, plus 1. And then I need the s squared term, so that 2 gives me a 1/2, so I should get 1/2 s hat squared plus this. Now let's see. Let me check my algebra here. Is that right? I think so. Yes, that's correct. Okay, so then here's my equation. So now that I have my equation, I think I go do what? Determine the roots. So let's go determine the roots. So when I look at this roots here, let's do it the other way just to be careful here. The other way that we could do it here is that we can compare this to what? S squared plus 2 alpha s plus omega not squared equals to 0. So what do? I'm going to calculate alpha using this. So if I just compare these two, you see that I get 2 alpha equal to 4, and I get omega naught equal to 2. Right? Is that? Let me see what I got. My solutions tell me I have a mistake. Where's my algebraic mistake here?
It's 4 pieces. No, down. There are this 4 is not 2.
So that's 2, and then that's 1/2.
So then you multiply everything by 1.
Yes,
That would be negative 3, not plus 1.
this one?
No, you use negative 2 times 1, negative 2, minus 1.
But remember, I took off the minus sign. I had an error. Let's go look at this here one more time. Right? This has to be true. So I get a quarter VC. That looks good. This guy, 2. That looks good. So when I come over here, it's got to be VC plus a quarter S hat. Okay? This guy looks like 1 minus 2 S hat. I think that looks good. Let's do the multiplication now. So if I multiply these two, I'm going to take that minus 2, put it right there. I get 1 plus 4s times s. That looks good. And then I get the minus 1. Okay? So if I multiply this out, I'm going to get 2. That's my term right there. My second term is 2 times a quarter. Gives me a half squared. That should be cool right there. But yet, I'm getting this relationship right here. I wanted to do a critical. And I'm showing that I don't have critical. Well, maybe we could pretend for a little bit. Where did I mess up on my... I keep telling me that I get a 2 here. Yeah. So So I think that's not what I wanted. That's not what I wanted. So if I look at this guy here, you can see that in this case, I'm going to get that alpha is greater than omega naught, which means that it's overdamped.
Yeah.
Is alpha is 2.
Right? And I'm going to say, I'm not going to go any further.
Let's look at the matrix.
I wanted to do critically damped, but my solution tells me it's over.
This would just be negative 2x
Say it again.
minus 1 x minus 1. What's over to the negative 2?
If I make that resistor 1/2, well, I'm not going to come to it. So, dude, what happened to the 10 minutes per problem thing? And we still got step 3 and 4. Isn't that sweet? We got a busy Wednesday. Okay, I will see you on Wednesday.